Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section, we're going to continue developing our skills with trying to understand when series converge and when they do not. And we're going to talk about the comparison test, the so-called comparison test of series convergence. So in the last section, the main thing that we introduced was the integral test, which is basically you can take the integral of the equivalent function that would look like the terms in a series, and if that integral converges, then the series also converges, okay? And we know how to take integrals, so that's sort of a pretty bulletproof way to figure out if a series converges or not. Unfortunately, sometimes the integrals are going to be hard to find by hand. You know, there's lots of integrals that you can't ever find by hand. You have to use a computer to find them, and so it's not very helpful if you can't calculate the integral. It's not very helpful to figure out if the series converges or not, because maybe you can't integrate the thing at all. Okay, there's plenty of integrals you can't do. So in this section, it's called a comparison test, and that is because what we're going to do is we have the series that we want to look at and study and figure out if it converges. That one's called a sub n. Okay, and what we'll do is we'll look at another series. We'll make one up. It'll usually be related to the original series we're given. But what we'll do is we'll look at a related series, and we will see if that series converges or not, and we'll look at the behavior of that series, and under certain conditions, by comparing the series we're interested in, that we don't know anything about, to a series that we do know something about and how its behavior is, under certain conditions, we can figure out if the original series that we care about converges or not. There's some very specific things that have to be true, but if you can show that those are true, the comparison test is pretty easy if you can do that, and it's pretty powerful and pretty simple. So let's just jump into it. Okay, the comparison test. Okay, the comparison test. What is it? What are we going to do? We're going to say the following. We're going to say, suppose that the two series a sub n. This is the series that we care about. This is the series given to you in the problem to look at, okay? And Bn, this is the series that we're going to use to compare it to, okay? Have positive terms. So far as all it's saying is, suppose we have two series, the series that we're given and some other related series that I haven't told you anything about how to find, but let's just say that these two things have positive terms. What we're going to end up doing is comparing them, and we're going to learn something about our original series by studying a related series. That's what it's telling you, okay? So, part A, okay? If, and here's where the rubber meets the road, if the series B sub n, the one that we make up to sort of study, okay, to see how it behaves. If Bn is convergent, and, this is a very important and, the terms A sub n is less than or equal to B sub n, we'll talk about this in a second, for all n, I'm going to underline that, for all n, then the series that we cared about, A sub n, converges. Okay. A picture is worth 1,000 words, and so I'm going to do that right here. Okay. Let's say this is a little xy graph here, and this is n, and this is you know, the term in the series that we care about. Okay. Let's say I'm trying to study. Let's say I'm trying to study A sub n, which is a series, right? And let's say that the you know, n is equal to 1, 2, 3, 4, 5, 6, 7, whatever. You know that the terms of A sub n do something like this. They approach 0. But that's not enough to tell you if the thing converges or not, just if the terms approach 0. You must have the terms approach 0 in order for the thing to have a hope and a prayer of converging, but it doesn't tell you by itself. So these things are A sub n's. These are the terms of the original series I care about, A sub n. Okay? Now, let's say that I make up, I'm going to just pull out of thin air. It doesn't even matter where I get it from, but I'm going to make up another series, okay, that's going to have terms that are all larger than the one I actually care about. So these terms are actually bigger. If you look at the elements that you're adding up together, each element is a finite amount bigger than the one I care about. Okay? That's why it says A sub n must be less than B sub n. A sub n must be less than B sub n for all n, every single value of n. So it must kind of parallel as it comes down here then. So what this thing is saying is, let's just read it. Suppose the two series a sub n and b sub n, which are given here on the graph, have positive terms, which they do, if b sub n, which is the blue dots, is convergent. If that series converges and a sub n is less than b sub n, like I've drawn it here, for all n, then you have proven that a sub n converges. Another way to look at it is, look, I've got two related series. The red series is the one that I care about. That's the one given to me on the test. The blue series, I have chosen it so that all of the terms are actually larger. Every term that you add together is a little bit bigger than the corresponding term in a sub n, okay? If I prove that B converges, the blue line converges, then because you can kind of think of it this way, because it's on the top, in other words, it's bigger, it's on the top, it kind of squeezes a sub n, and that's how I think about it. If it's on the top and it converges, it forces a sub n to converge because you've proven that a series even larger than a sub n is convergent, and so it kind of squeezes a sub n. So that's how I memorize this when I do it myself. You pick another series whose terms are all individually larger, and if you show that that series converges, then a sub n must converge because it sort of squeezes it. It sort of squeezes it. Now once you understand that, part B is exactly the same thing, it's just in the opposite, okay? If the terms of B sub n, the series B sub n, diverges, and a sub n is greater than or equal to b sub n for all n, then I have proven that the series I'm interested in, a sub n, diverges. Okay? Now let's draw a picture, because again, a picture's worth 1,000 words. Okay? So we're going to do the same thing. Here, it's a little graph. This is n, and then this is the value here that we have. Now, in this case, 1, 2, 3, 4, 5, 6, 7, we have infinite number of little elements. And again, I have a series, okay? And I have the elements here like this, okay? I have the elements here like this. And what I'm saying here is, in this case, b sub n is less than a sub n, or you can read it this way, a sub n is greater than b sub n for all n. So in that case, for my blue dots, this is the series that I invent myself. All of the elements that I'm adding together must be a little bit smaller than a sub n. So what we're saying here is exactly the opposite of what we're saying up above. If you choose a series, an equivalent series b sub n that you pull out of thin air, and if you can show that every element you add together in b sub n is less than the corresponding element in a sub n, so it's below a sub n instead of being above like it was before, and if you prove that b sub n diverges, in other words explodes and goes off to infinity, then you have proven that a sub n also diverges. And you can kind of look at it the same way. B sub n lies below a sub n. The B series lies below the A. That's what this is saying. So if B diverges, it kind of pushes A off to infinity. So you have found a series that lies below the one you care about, and yet it itself diverges. So you've proven that the one you care about also diverges. So these are things that if you read in the book, it can be a little bit difficult to understand what they're saying, but I'm hoping that the pictures here make sense. Basically, you have a series you care about seeing if it converges or not. You pick out of thin air, and I'll show you some tricks to do that, another series, b sub n, where every single element that you're adding together is larger than the a sub n that it corresponds to. If this guy converges, you can think of it pushing on a sub n, and so then a sub n also converges. But if you find a b sub n that's below the series you care about and it diverges, then you have proven that a sub n diverges. And that's all these two things are saying, and that's called a comparison test. You're inventing another series that you understand, and you're comparing it to the one you care about. And by the way, usually, a lot of times, you'll be picking a P series or something like this that you understand quite well, if it converges or not, in order to compare with the original series. Okay, now we're going to get started with our first problem. What if we have the sum n is equal to 1 to infinity of 1 over n cubed plus n squared? Okay. The first thing is, does this look like a geometric series or a P series or anything else that we've studied that's easy? The answer is no. Okay. You might be able to find out if this thing converges by the integral test. I mean, it looks like you could probably integrate this thing But the point is here, some of these series have multiple ways to figure out if they converge or not, and we're not going to do an integral test here because we've already studied that. So we're going to try to use a comparison test so that you can get some practice with it. So what we have to do is find another series that I know the behavior of, and I know how it looks in relation to these terms, and then I can use this theorem over here, the comparison test, to find out if this one works or not. So what you're usually going to do is you're usually going to look at the terms in the original series you have to find the series to compare it to. So in this case, I think it's better just to go by example and say, okay, I'm going to actually change colors here, and I'm going to pick blue because blue means B sub n, right? B for blue. So the B sub n that I care about, okay, what I'm going to do for that one is I'm going to say that's the sum from n is equal to 1 to infinity of 1 over n cubed. You see, it's similar. It's part of the original series here. I can pick any B sub n I want. I'm free to pick anything I want. But the trick is, in order to use the theorem over here, you have to know, look over here, you have to know if the elements of the series you pick are higher or lower than the series that you're studying. So by picking a portion of the series you're studying, you can kind of figure out which one's bigger and which one's smaller. Now let me ask you this, is A sub n bigger or B sub n bigger for a given value of n? Okay, the answer is, in this case, A sub n is less than B sub n. Because look, for any value of n, I'm going to have a bigger number down here. So this is going to be a smaller fraction than anything I would put in here. So A sub n is less than B sub n, okay? So I'm in the case, okay, just to kind of draw it, I'm in the case where if I had A sub n that looked like this, okay, then B would be above it, okay? Because what we're saying is A is less than B for all values, okay? So the series that I have chosen here, which is sort of looks like part of the series I had, is for every value of n greater. So let's find out how this thing behaves. How does Bn work? Well, look at the guy here. It is a p series, 1 over n to the third power. So what you would say on your test is B sub n, okay, is a p series with p is equal to 3. And notice if you go back to the p series, if p is greater than 1, then we know that B sub n converges because p is greater than 1. And so because B converges and because B is on top, it squishes A sub n, so we have proven by the comparison test that A sub n also converges. And this is how I would write it down in my test. I would say B is a p series, all elements of B are greater than A, and since B is known to converge because of its behavior there, with P being equal to 3, and because it's on top, it sort of squishes A sub n, and A sub n also converges, okay? So by the comparison test, A sub n converges, which is this series right here. This one converges. Okay, the next one is, what if I had the sum from n is equal to 1 up to infinity of 3 over n times 2 to the n, okay? 3 times n times 2 to the nth power. Now this doesn't look like any kind of series that we've studied before. I mean, you kind of have an exponent here, but this n out in front is going to clobber it from being any kind of p series. It doesn't look like anything we've really studied. So we're going to try to use comparison test. And I'm going to compare it to the following b sub n. I'm going to compare it to the following series. N is equal to 1 to infinity, 1 over 2 to the nth. Okay, I'm going to pair it to that. Now let me ask you this. I can make up any Bn I want, but look, I chose a part of the original series, and I do that because it lets me figure out which terms are bigger, which is what I need to know. So if I were going to figure out which terms were bigger, think about it. If I put values of n that are very large in here, okay, if I put values of n that are very large, I'm going to get a smaller number than I would get here because I have more n's on the bottom. I'm going to get 3 over a larger number, I should say, larger number on the bottom, which is going to drive this thing lower. So you could say A sub n is less than B sub n. For any value of n, A sub n is going to be less than because I'm going to have a larger denominator. Okay? So if you were going to draw it in graphical form, what it would look like, okay, is the original series that I cared about was A sub n. So I would have some dots here at the various values of n. And the series that I have invented to compare it to would be on top, just like before, because the terms are just laid out that way, okay? Now let's look at b sub n and see what kind of series it is. It looks very familiar, but it is not a p-series, because a p-series is 1 over n raised to a power, and this is 1 over a number raised to n. If you go back and look at the geometric series, it is a geometric, or it looks like I should say it looks like a geometric series, okay? The geometric series, remember, the geometric series, just recall, it looks like n is equal to 1 to infinity of a times r to the n minus 1. That is what the geometric series looks like. Now let's see if we can beat this thing into that shape, okay? So if I say b sub n is equal to sum from n is equal to 1 to infinity, okay? This is going to be 1/2 to the nth power. I can definitely do that because I have a 1 on the top, so bringing that n out is going to give me exactly what I have here. Let me see if I can simplify this. Sum from n is equal to 1 to infinity. Let me go ahead and assume that it is a geometric series. So I'm going to have 1/2 to the n minus 1. I'm going to have an n minus 1 to make it match with the geometric series definition. But I've changed the series, so in order for this to happen, I need to put a 1/2 with some exponent here, which is going to end up being 1, to give me back what I had. So I'm going to assume it's geometric, I'm going to make it in that form, but then I have to add this, because now if I were to do this multiplication, I would add the exponents and I would get back what I had started with. So in order for this to be a geometric series, the 1/2 comes out, and I have a summation. N is equal to 1 to infinity of 1/2 times n minus 1. Okay? Now this is a geometric series, okay? And the inside here is less than 1, okay? Is less than 1. So what you're saying here is the guy inside the parentheses here, which is r, in terms of the geometric series, is less than 1, and if you go back to your geometric series, that means that the geometric series b sub n that we created converges. Okay? The sum over b of n, that series, converges. And because it converges, and because it lies on top of, for lack of a better word, a sub n, you have proven that by the comparison test, a sub n converges. Okay, so it's the same exact process as last time. I have an a sub n that I'm studying, and I invent the b sub n to compare it to. I just happen to choose a portion of the series there to help me out there. The reason I do that is because it's easy for me to figure out which terms are bigger when I choose a portion of that series. Okay, and I know from just inspection that b sub n has larger terms, so it lies on top, and I know that it's a geometric series with the r being less than 1, and if you go back to that lecture on that, you'll remember that that case is the case when r is between -1 and +1, when the geometric series converges. So because it's on top, and because that series I made up converges, it proves by comparison that a sub n also converges. And just to be totally rigorous about it, when you're talking about series like this, you really should say the sum over a sub n converges, so that you're very clear that you mean the series actually is the thing that goes off and converges. Okay, so moving right along, if you had the sum of n is equal to 1 up to infinity of 3 over n times n plus 1, okay, actually I'm going to make it n plus 3, okay, n plus 3. So I want to see if that guy converges. It doesn't look like a series that I've seen before, but before I go any farther, what I want to do is I want to expand what is in the denominator. So it's going to be n squared plus 3n, okay? So all I did was do that because I want to have it all laid out and expanded in front of me. And it doesn't really look like a p-series or a geometric series or anything. I could integrate it. I mean, I could try to integrate it if I could find a way to integrate it with the integral test to see if it converges. That's going to be an interesting integral to try to solve. But we're not doing that here. We're doing comparison tests. So what should we choose to compare it to? My first instinct is just to compare it to 1 over n squared, okay, because it's convenient and it looks like it's an easy way for me to see which terms are bigger than the others. So I can say that the b sub n terms, okay, are going to be equal to the sum of n is equal to 1 to infinity, 1 over n squared. So the b sub n series is equal to that. Now, does that help me here? Can I figure out which terms are bigger? Okay, if I'm looking at the terms here, okay, what am I going to have here? For any value of n, I'm going to get a larger denominator here than I ever would over here, okay? And that's going to mean that these terms are smaller, right? It's going to mean that those terms are smaller, so that a sub n is going to be, again, smaller than b sub n. Okay, that's what it means. For every value of n, this is going to lead to a smaller number because the denominator is larger. So using our colors like we've been doing, the original a sub n would be these terms. Okay, and then we have shown that this b sub n that we pulled out of thin air is going to have larger terms. So it's going to sit on top. So we need to find out if it converges or not. Okay, if it converges, it'll squeeze the other guy down. Okay, so what we're going to do next is we're going to look at this and we're going to say, what kind of series is that? Okay, 1 over n squared. What kind of series is that? Well, it looks like a p-series to me. Okay, it's a p-series. So what you would say is b sub n is a p-series with p is equal to 2. And if you remember, when p is greater than 1, it converges. So sum of b sub n converges. So you have proven that this series that has every term larger converges and it squishes a sub n down and proves that a sub n also converges. Okay? So you take the original function, you try to find one that is related to it. We looked at the highest order here in the power and we just sort of took a guess and tried. You could pick another series if you want to, but that one looked attractive because when we picked it, we could easily find that all of the elements were greater for every value of n, and we also knew if this thing converged or not, and so we proved that a sub n also converged. Okay, so in the last few problems we talked about the comparison test where we chose a series that's usually related to the original series, and we looked at the behavior of that series in order to figure out if the original series converged or not. Okay? The trick is sometimes finding a good b sub n series is hard. Sometimes it's not so obvious what to choose, or let's say you choose one but you don't know if that one converges or not, so it isn't very helpful. The examples that we had before, it was pretty easy to find a series that we knew if it was bigger or smaller than the original series, and we also knew if it was a p-series or a geometric series, so we could apply the theorem. But it's sometimes very hard to find a good b sub n that works. Okay, so there is an alternative comparison test out there. It's called the limit comparison test. I'm not going to prove it or really get into the details of why it works. Okay, it's one of these things you have to memorize and do, unfortunately. So I'm going to write it on the board. We're going to work a few problems and get some practice with this. So it is also a comparison test, but it's a different theorem that you can sometimes apply, and it ends up looking at taking the limit of the ratio of the a sub n terms and the b sub n terms. Okay, we have the limit comparison test. The limit comparison test, okay? Suppose a sub n and b sub n, the two series here that I have, this is the original one, this is some series I make up to look at the behavior of, are series with positive terms. Okay, same thing as last time, they both have positive terms. Okay, then we have three little subparts. Okay, if the limit as n goes to infinity of the elements a sub n over b sub n, the terms, is equal to some number, it actually converges to some number greater than 0, okay, then either both series converge or both series diverge. Okay, again, I'm not going to prove it. You'd have to go to quite a few lengths to actually prove it. But basically, we have the series that consists of an infinite sum of the elements of a sequence that we care about. We pick some b sub n series, and again, we're going to usually pick b sub n to have elements or have characteristics of the original series. Okay. If we take the ratio of the a sub n's to the b sub n's, which are the elements we're adding together, and we take the limit, so we're going to be taking limits in this section, if that limit is equal to a number greater than 0, then it means either both of these things converge or they both diverge, okay? So if you can find b sub n converges, then you approve a converges in this case. and vice versa. But both of these things have to be, both of these things are true if the limit converges to a number, and that number has to be greater than 0. Okay, so that was part A. Now over to part B. Okay, if the limit as n approaches infinity of a sub n over b sub n, the elements, is equal to 0, exactly equal to 0, okay, and Bn converges, okay, then a sub n also converges. Okay? So it's another if statement. If the ratio of the terms, and these are the terms, by the way, these are not the summation, this is just the ratio of the terms as n goes to infinity approaches 0, and you can prove that b sub n converges, then a sub n also converges. Okay, now part C. And this is the final part. If the limit, I bet you can guess, n approaches infinity of a sub n over b sub n is infinity, so it diverges. Okay, so if the ratio of the elements here goes to infinity, and you can prove that the sum b sub n diverges, then the original series you care about also diverges. Okay, now unfortunately you're going to have to memorize this. That's just the secret. I'm not going to lie to you about it. It's not fun to memorize things, but you're going to have to do that. Okay, this is a limit comparison test. It's one of those things you really, when you work your test, you should go through them in order. Okay, let me see if it's a p-series. Let me see if it's a geometric series. Let me see if it's a if I can use the integral test. Let me see if I can use the comparison test. Okay, let me try the limit comparison test. And the limit comparison test is you have the original series you care about. You make up a new one with elements or characteristics of the original one. I'll show you how to do that. You take the ratio of those terms and you take the limit. If that limit comes out to a number greater than 0, then either both of these things converge or they both diverge, and so you're usually going to be able to figure out if B diverges or not, and that'll tell you if A diverges or not. If you take that limit and you get exactly 0, but B sub n converges, then A sub n also converges, and if you do that limit and you get infinity, and B sub n diverges, which means it goes to infinity, then A sub n diverges as well, okay? So they're a little bit symmetric. There are 3 cases. You really should write them down and try to memorize them, and we're going to work some problems here to get some practice. So let us say we have the sum from n is equal to 2 to infinity of the square root of n over n minus 1. Okay, now the fact that this goes from n is equal to 2 to infinity doesn't really matter, you see. I mean, they'll probably give that to you in your test just to see if you get you know, choked up over that little thing. I mean, yes, it does make the series different, but we're not talking about, we don't care about what the thing adds up to. We care if it converges or not. So the fact that there's an extra term missing doesn't matter. That extra term is not going to make the thing diverge or not. It's the behavior as you go to infinity. So really just keep that in mind, okay? So what we're going to do is we're going to try to choose a b sub n. That's the first thing. This is a sub n, and we're going to try to choose b sub n because we want to find something to compare it to. My recommendation to you when you're using the limit comparison test is to choose b sub n by retaining the highest powers in, oh, I should say of, a sub n in the numerator and denominator. Okay? It's a lot of words, but it's really easy. What it says here is what I'm going to do is I'm going to say for b sub n, I'm going to say it's the sum for this particular example. Okay? Let's go back up here for just a second before you choose b sub n. Let's simplify this. Sum from n is equal to 2 to infinity of n to the 1/2 over n minus 1. I like to write everything in terms of exponents, okay? So I'm going to retain the highest power in the numerator, which is n to the 1/2, and I'm going to retain the highest power in the denominator, which is n. Okay, so that's what my bn is going to be, and that's going to be my first starting point. And you can actually simplify this, and this is going to be 1 over n to the 1/2, because you can subtract the exponents there, and you get 1 over n to the 1/2, and it's going from n is equal to 2 to infinity because it has to start from the same place as the original series that I had, and so that's the other b sub n that I'm going to use. And I'm going to do the limit comparison test. So in order to do that, I need to take the limit as n goes to infinity. You see, it matters how n goes to infinity of a sub n, which are the elements of A, and b sub n, which are the elements of B that I'm adding together. Okay, so that's going to equal the limit as n goes to infinity. A sub n is equal to n to the 1/2 over n minus 1, and I'm dividing that by b sub n, which is this, 1 over n to the 1/2. Okay, so let me simplify this. We're going to have limit as n goes to infinity. Okay, I'm going to take this fraction, flip it over, and multiply it. So I'm going to have n to the 1/2 over n minus 1 times, flipping this fraction over, n to the 1/2 over 1. All I did was flip it over and multiply. I haven't even done the multiplication yet. Limit as n goes to infinity. This is just going to give you n because I'm adding the exponents, and this is going to give you n minus 1 because you're multiplying by 1. So it's n minus 1. So what you're getting in the end is a limit of n over n minus 1 as n approaches infinity. Now, what does that limit actually evaluate to? Well, I'm going to have infinity over infinity. If I try to plug infinity in there, I'm going to get infinity over infinity. So I need to use L'Hopital's rule, okay? Which means I can take the derivative of the top and the derivative of the bottom. The derivative of the top here is just 1, derivative of n is 1, and the derivative of the bottom is also equal to 1. So this is just a number, which is 1, and so as I approach infinity, the answer is 1. So we have found that the limit of the ratio of the elements, which is what the limit comparison test is, does converge, and it converges to 1. So let's back up here. We're in case A. If the limit as n approaches infinity of the ratio is equal to a number greater than 0, which is exactly what we found there, then either both of these things converge, a sub n, b sub n, or they both diverge. So then now what we need to do is go figure out if we can find out if b sub n diverges or not. Okay, so what does b sub n do? B sub n, what kind of series is that? Okay, it is a p series. It is a p-series, and that's why I say learning the p-series and the geometric series is really important. It is a p-series with p less than 1, okay? And so that means, if you go back to the definition of the p-series, if p is less than 1, then we have proven that b sub n diverges, okay? So the way I would write it on my test, because, I would exactly say this, because limit as n goes to infinity of a sub n over b sub n was equal to 1, and we found that b sub n diverges. Okay, going back over here, we're in case A. Either both of them converge or both of them diverge, and we found out that B diverges, so that means that a sub n, which is the one that we cared about, also diverges. So it really just boils down to finding out a b sub n, okay, and going off and figuring out if that b sub n converges or not, and then figuring out what the limit of the ratio is and figuring out what case you're in. And it's sort of cookie cutter. It's something you have to memorize, but once you find out the limit of the ratio, which is usually pretty easy, find out if the b sub n converges or not, and then go over here and figure out what case you're in, and you'll prove if a sub n converges or not. Okay, our final problem is going to be, what if you had sum of n is equal to 1 up to infinity of n over big square root n to the 5th power plus 4, okay? Well, the first thing I'm going to do is I'm going to try to find a b sub n, okay? Try to find a b sub n, but before I even do that, I never like radicals running around my series. So it's 1 to infinity of n over n to the 5th plus 4 to the 1/2, okay? That's what I have. And I'm going to try to find b sub n, and remember what you want to do for b sub n is you want to try to retain the largest powers of the exponents in the top, the terms that contain the largest powers of the exponents in the top and the bottom. And so what you're really going to do in this case is you're going to try to find b sub n is then going to be equal to, b sub n is then going to be equal to, the largest power on the top is n, and the largest power on the bottom is n to the 5 halves. Now that's 5 halves because it's n to the 5th power, but it's got a radical around it, so you kind of have to do that too. There's no dirty, quick and dirty rule that always tells you exactly what to choose for b sub n. It's only a guideline. You can choose anything for b sub n, but it's useful to choose the highest powers in the top and the bottom, and in this case you just want to keep the square root around because that's effectively going to chop down that 5th power there. So it's n over n to the 5 halves, okay? So the next thing you want to do is you want to go off and see if this thing converges or not, okay? You can see that this is going to reduce to 1 over n to the 3 halves, okay? You can see that it reduces to that because basically what you're doing is you strike this out and you're subtracting 1 from the bottom. So 5 halves minus 1, you would have 5 halves minus 1, which is going to be 5 halves minus 2 halves, which gives you the 3 halves on the bottom. So what you're doing is you're just subtracting the exponents there to get that. So this is a reduced form of b sub n, and we're going to work with that reduced form. So we had the highest powers in the top and the bottom, we just reduced it. Now what we want to do is find the limit of the ratio of these elements. So the limit as n goes to infinity of a sub n over b sub n, which is the limit as n goes to infinity of a sub n, which was this, n over n to the 5th power plus 4 to the 1 half, all over what I found for b sub n, 1 over n to the 3 halves, okay? And what I want to do is figure out what that limit equals. So let's go ahead and do that. Let's flip this guy over and bring it onto the top. So it's going to be limit as n goes to infinity of, when I flip it over and multiply it, I'm going to have n times n to the 3 halves over, flipping it over, the denominator here, which is n to the 5th plus 4 to the 1 half. Okay? So continue simplifying. Limit n goes to infinity. On the top, I'm going to add the exponent, so n to the 5 halves over n to the 5th plus 4 to the 1 half. Okay, and what I want to do is I want to try to see if I can figure out what this limit is equal to. Okay, now notice I have n to 5 halves on the top, and I have something with a radical on the bottom. So I'm going to keep on beating this thing into shape so that I can actually do something clever here to figure out what this limit is equal to. This is going to be limit. I'm going to write the top as n to the 5th power, and I'm going to raise that to the 1/2 power. And notice when I multiply these together, I get exactly back what I think I should have. And on the bottom, I'm going to have n to the 5th plus 4 to the 1/2. And I think you might see where I'm going with this. The reason I'm doing this, okay, is because I want to bring all of this stuff under the common radical into the 5th, n to the 5th plus 4, all raised to the 1/2. You see, now that looks a whole lot cleaner from the point of view of doing a limit, because now I can simplify this guy by dividing the top and dividing the bottom by n to the 5th power. So n, the limit of n going to infinity of, how can I simplify the top? If I divide the top by n to the 5th, I'm going to get 1. And if I divide the bottom by n to the 5th, I'm going to get 1 plus 4 over n to the 5th, all to the 1/2 power. Now notice that I haven't changed anything. I'm dividing the top by the same number I'm dividing the bottom by, and when I divide the top by n to the 5th, I get 1. When I divide the bottom, which is this whole thing, by n to the 5th, first term becomes 1, second term just becomes divided by 4/5. Now, finally, why did I do all of this? Because now I've got it in this form. If I take n off to infinity, this little term is going to go to 0. 4 over infinity is going to go to 0. So I'm going to have 1 over 1, which is 1. I take the square root, which is just going to give me a big fat 1. Okay, so where do we stand? Going back over here, we're in this case here because we took the limit of the ratio of the elements and we got a limit greater than 0. So now we're in the case where either both series converge or both series diverge. Okay, that's the case we're in, and so we just need to figure out what case that is. Look at what b sub n is. B sub n is a p series with p greater than 1, and I think if you remember back, that means that it converges, okay? And so since the p series converges, then since both series either converge or diverge, since we've proven b sub n converges, we know a sub n converges. So the way you would write it down, if I were actually writing this on a test, is I would say since the limit of a sub n over b sub n is equal to equal to 1, which is a constant greater than 0, which is what's stipulated in part A over there. And we know that b sub n converges because it's a p series with p greater than 1, and that's when p series converges. Then we have proven that a sub n converges. We have proven that a sub n converges. So you're just picking another series with the highest powers in the top and the bottom. We're beating it into shape. This one was a little bit different because it involved so much algebra, and the reason you had to do that is because you had a ton of radicals everywhere. You had this ugly radical from the very beginning, and so when we found what b sub n was, and we had ugly exponents everywhere, but the kicker was when you got here, the epiphany of the whole thing is that you said, okay, I have 5 halves on the top, 1 half on the bottom. This is n to the 5 square root, and this is a square root term. So let me split it up here. And then when I do that, I can combine them all under one common radical, and then I can do some more simplification, get it into the form where I can take the limit very, very efficiently. So in this section, we have covered something very important, which is the comparison tests. And what we're doing is we're basically picking another series that's generally related to the series we care about. And in the first type of comparison test, we're looking if we're trying to find a series that either lies all above the series we care about or all below, and we're looking if that behavior of b sub n, and if it squishes it down, then it forces it to converge, and if it's underneath, then it blows up and it kind of pushes it up, and then it can force a sub n to diverge. It doesn't really force anything to converge or diverge, it's just an easy way to remember it, okay? When you pick the series, if it's under or above, and if it goes down and squashes it, or if it pushes it up to infinity, okay? And then we also had the limit comparison test, where we're picking a b sub n, again related to a sub n, and we're just using the theorem in the different cases there. We're taking the ratio of the terms of the series, and we just have different cases there that tell you that if the limit exists or if the limit doesn't exist, then you can try to learn some things about b sub n, which will tell you about a sub n. So there's no silver bullet to this stuff. I mean, that's why Advanced Calculus 2 is pretty tough, because in these sections you're learning all of these different ways to test for series convergence. And sometimes it's hard to know what to use. I mean, it really is. Especially when you're on a test, when you have all of them in your tool bag, and you really don't know what he wants you to use, what the teacher might want you to use. And so either you see it or you don't. The only way you can get there is by working a ton of example problems, get some experience, okay? And then when you're on your test, run through your list. Is it a geometric series? Is it a P series? Can I use the limit test? Can I take the integral of the thing and see if the integral converges? Can I find another series that looks similar to it that might squish it or something that I can compare it to? Can I take the limit of the ratio? And then we're going to have some other ones that we're going to learn about in the next few sections that you'll have as well. Can I do this? Can I do that? And it's not fun sometimes to do trial and error, but a lot of times you have to kind of do a few different things to see, and eventually it'll pop out at you and you'll say, well, this is the one that works. Okay, this is the answer. So that is how to do the comparison tests when trying to find series convergence in advanced calculus.